You want to add? You feel like adding? You want to do some adding? You want to add a whole bunch of things? You need sigma notation. This is a way of representing really, really long addition problems. So it's not adding anything super exciting. It's a pattern that gets added over and over and over again. Is there a way that we could abbreviate that process? And that's what that is. So we've got a bunch of formulas down there for dealing with squares and cubes and just regular things and constants. And yeah, it's gonna be neat. It's gonna be neat. I will say that the algebra of this stuff is gonna be very intense. Think about it as when we first learned the uh, the long version of doing the derivative using a limit. That's where this is going to come in. Doing the anti-differentiation by hand requires these, well, not by hand, but like the long formal way. However, it is not super tested on the AP exam. They could do stuff with sigma notation and give you things that are similar to this, and I expect you to kind of digest it into integration. So that's why I'm going over this. But we're never going to do really doing them by hand outside of this video. Now, in this example, they haven't asked us to figure out a certain number of rectangles. Man, I cannot stop saying triangles. Um, we want to figure out what's going to happen as we put more and more J's or whatever into this one. So we want to do a little bit of simplification here using those same tricks as before. So so this equals, well, that n squared, we're going to put in numbers for that. That's going to be fixed at 10, 100, 10,000. We're going to fix those numbers. So it's not going to be increasing like we had before, like 1, 2, 3, 4. That's what j is going to do. So that n squared is just a constant. Yeah, it's a variable right now, but I want to think about it as a constant, like a 10. So that equals 1 over n squared. And then the summation, I'm just going to write the summation, 7j plus 4. And then we can break that up into two chunks. So 1 over n squared. And I'm going to bring the 7 in front too. So this piece right here becomes 7 summation j plus the summation of 4. And remember, we're going to some n value, so that's multiplied by whatever the n thingy is. So that's going to be 4n. And then just a j. What is just a j again? So if it's just an I, it is n plus 1 over 2. N plus 1 over 2. So this is 7 times n plus 1 over 2. They're using a j here instead of an I. It means the same thing. And then this is all being multiplied. Oh, there's a plus. 1 over n squared. Okay, so let's clean this up. So I'm going to distribute that n squared in there. So that's 7n plus 1 over 2n squared plus 4n over n squared. So let's see, that is 7n plus 1 over 2n plus Oof, 4n. All right, common denominators. So that is 8 over 2n. So that is 7n plus 7 plus 8 over 2n. So that summation thing from up above, let me go steal it. Gimme, 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 gimme. So we can simplify the summation down. No! Want this stuff. I want this stuff right here. Yeah, yeah, yeah. No, no. Come here. All right, great. All right, great, great, great. So this thing equals stuff. 7n plus 15 over 2n. Great. Now they want us to put different values in there. So let's use our calculator to do that. Let me show you a trick. The first one they want us to do is 10. So we're going to have 10 and we're going to store that using this store button. And then, well, I want to use X just because I have a nice button for X. So I'm going to say, hey, calculator, remember, if I write an X, that means 10. So that's what that store function does. So watch, if I do 7 times X now, it understands that's 70. So that way I can just kind of like do my 7x plus 15. It like we're doing kind of normal numbers right now, but that store function is kind of nice if you've got some weird thing that you're trying to have it remember for a while. Divided by 2x. This way I can sneak different values in there pretty easily. Okay, so when it is 10, we get 4.25. But the next one they want us to do is 100. So I'm going to do 100. I'm going to store that as x. Okay, calculator, remember that. And now I can just do second enter a couple times. So I can just get this back, and then I can figure out what the next one is. So when n equals 10, the summation was 4.25. When it's 100, we get 3.575. If we make it 1,000, we get 3.50075. Now, what's interesting is this is wrong. 3.575, and then this was 100. And then when we did n equals 1,000, we get 3.50075. So when we went from 10 to 100, it changed a lot. Like it changed by like 7/10. But then when we squared that, it didn't really change by all that much, like 7/100. And I bet if we keep doing that and we keep increasing that n value, then it's going to stop changing and it's going to kind of zero in on just one thing. Have we done that before? Something about a value getting bigger and bigger and bigger, but then it sort of stops changing, like a limit. Now, this is where it gets real weird. We're going to state this Riemann sum, and it's going to be a very special Riemann sum. And it looks like it's weird, crazy stuff, but it's what we did before. This is our rectangle. We've got this rectangle here, and it is delta x sub I. And then going up the side, that is our f of whatever our c value is. So that is our kind of height of our rectangle, and then our width of that thing. And so we're trying to do a summation of all those thingies. What this also is trying to talk about is you can set this up so it kind of varies, because like as the curve is moving, like you might want wider rectangles or narrower ones. It's kind of goofy. It's not super important. About the norm partition means that everybody's the same, but this lets it be different sizes. It doesn't matter for the purposes of what we're doing. But if you ever see this norm partition, this word really threw me. This norm partition thing just means, hey, all of the thingies are the same width, which is usually how we've been doing our rectangles anyway. Okay. The definite integral. This tells us the exact value of a curve as we make a whole bunch, not just 100, not just 1,000, an infinite number of rectangles. If we make an infinite number of rectangles, what happens is the value stops changing and it starts locking in on a particular value, and we can find a definite value, just like we could do with a square. We can find the area of a square. We can find the area under a curved shape. Now, when we learned derivatives at first, there was the limit version of it. We did it for about a day and then we abandoned it and never did it again. These, even less. Like, they're not really going to test you on it, but they may give you some gobbledygook like this, and you need to be able to recognize that gobbledygook as being a definite integral. But you do not need to do this to find a definite integral. That is not how we're going to find it. But I do need to show you this so that you can recognize all of this gobbledygook as being a definite integral. Okay? That's it. You do not need to actually do it. I am going to do one in a video so that you can see what it's like to do it, but you will never actually have to do it. Okay? I'm just going to do it in a video so you can see what it looks like. You can throw up a little bit and then move on with your life. You do need to be able to recognize it. That's it. You don't need to actually do this limit. What we can do with that is we can figure out a definite integral to figure out what the area underneath this curve is. No rectangles, what the actual area underneath it is. So this definite integral would be something that's going from these two spots. So from -5 to 5, that's the values where this thing's going to be 0, of f of x dx. That will be the area underneath that curve. If we could figure out how to do that properly, so you could also write it as the integral from -5 to 5 of 25 minus x squared dx. If we could figure out how to evaluate that definite integral, I can't chop that up into circles or squares or trapezoids or anything. Then we could get the actual value of that. Oh, wouldn't that be neat? But we're not doing that right now. But we could using the limit gobbledygook, but you don't need to worry about that. Yep. So TLDR of what we were talking about today is there's this summation notation thing. It is a way of adding big things together. It's not something that you're tested on a lot. We don't need to have those formulas memorized, but it is what I needed you to understand how that formula worked so you can understand what is happening when we find a definite integral. When we're finding a definite integral, we are actually creating an infinite number of rectangles, not just 100, not just 1,000, an infinite number of them. And using those infinite number of rectangles, we are able to precisely figure out what the limit, what the integral is. Just like before, when we were taking bad slopes and we were trying to find the derivative, we shoved those points closer and closer together so we could figure out what the limit, what the derivative was at a single point using limits. We are also doing limits when we're finding antiderivative, but it's using an infinite number of rectangles, not trying to push 2 points closer and closer together. Yeah, that's it. Thanks for watching. I hope your brain is not too goopy. Bye bye.